is coming to the session to present. Okay. Okay. Art is coming to the session to present. Sure. Yeah, I think he said that it was all approved now. That we can do the live stream as well. I got that email. So good. Sure. All right. Well, we'll see. That it was all approved now. That we can do the live stream as well.
Hi.
I got that email. So
Will we be good to go on time?
all right. Well, we'll see. That it was all approved now. That we can do the live stream as well.
Hi.
I got that email. So
Will we be good to go on time?
all right. Well, we'll see. That it was all approved now. That we can do the live stream as well.
Hi.
So
Will we be good to go on time? Hi, can everyone hear me? That's good. Will we be good to go on time? I guess it's 8:30 here at least.
yeah, actually, we were just waiting.
That's good.
There he is.
Yeah. Will we
He's
be
on stage already.
good to go on time? I guess it's 8:30 here at least. That's good. Yes.
Hi.
Yeah, so if you can make sure that you are on air, if you look at your host tools, and then up to
Yeah.
Mhm.
the on air button, and then when you're speaking, also amplify your voice, and then you can self-mute when you're and
Sure.
everything else is set, so we're ready to go. Great.
Okay.
All right. Perfect. Thank you. Okay. Hi. Welcome to the session. My name is Niels Meyer-Krallen from Aalto University, and I'm happy to chair this session about XR audio reproduction and perception. First of all, thanks to the organizers again for making this full VR conference. I think it's a really great experience for all of us. And okay, let's start. The first speaker is Lior Madmoni from Ben Gurion University, and he will speak about beamforming-based binaural reproduction by matching of binaural signals. And if I understand correctly, all the ambisonics fans will have to be very strong now, because I think his method will be a way of binaural reproduction without encoding microphone signals into the ambisonics domain or SH domain explicitly. But if I got it wrong, he'll probably correct me. So the stage is yours.
Thank you. That's about right. First of all, can anyone hear me? Great. So thank you for joining in. So I'm Lior, and thank you for the introduction. So let's just begin. I'll start with a brief outline about what I'm going to talk about. So I'm going to give a very short introduction to binaural reproduction, especially because this is the third day of the conference, and it's probably things that you have already know. I will then present two approaches for binaural reproduction. Also briefly, the plane wave decomposition approach, which is based on the ambisonics format, and the beamforming-based approach. We will then continue talking mainly about the beamforming approach, where I'll be presenting current advances and limitations in the design of such systems. And then I will be present our proposed approach for how to perform binaural reproduction, mainly with general arrays, where we don't have a lot of directional resolution. I will then present some simulation results, and we'll conclude the talk. So let's begin talking very briefly about what is binaural reproduction. Very simply, I have a basic system here just to emphasize that what we need in order to perform the binaural reproduction is both the sound field and the head-related transfer functions, or the HRTFs, which will be denoted by H throughout this talk, with L and R for the left and right ears. Then the binaural reproduction system takes these two components, combine them somehow to produce the binaural signals, which will be denoted by P. So one way to do that is to simulate. To do that is to simulate the sound field using a computer, which means that we simulate or generate the plane wave density function which is a function of frequency and direction. And another way to perform the binaural reproduction is with in real environments, using measurements. So in this case, we have some kind of acoustic environment and a microphone array, which is depicted by these microphones. And then what we get from this system is some kind of pressure, which is measured by the microphone array, which will be in here denoted by this vector x. And our main concern in this talk is how do we go from the microphone signals to the binaural signals, currently assuming that we have the HRTF somehow. So this will be less of a concern in this work. So as I said, one of the very common approaches is to perform plane wave decomposition, meaning that we take the microphone signals and basically estimate the plane wave density function for each direction or frequency that we are able to perform this estimation. And then we simply multiply the HRTFs with the estimated binaural signals, sum the contribution of all throughout all directional space, and get the binaural signals. This can also be formulated in the spherical harmonics domain, where we simply have the spherical Fourier transform coefficients of the sound field and of the HRTFs. And this is also known as the ambisonics format, which is well studied and understood. However, usually it requires a relatively complex array, like a spherical array. Another approach, which is more flexible in terms of the beamforming-based approach. And what we do in here is we use a set of beamformers, in this case, capital D, different beamformers with different look directions. And then we get these D different outputs for each of the beamformers. And at the next stage, we simply multiply each of the outputs by some kind of a scaling factor, which will be denoted by these alphas. And we also multiply it by the corresponding HRTFs from the look directions, which correspond to from the directions which correspond to the look directions of the beamformers. And then we sum the contribution from all of the directions, and the output is our estimated binaural signal. So we can write down the equation for this block diagram with this one here, and we will see that in later slides. And the uses for this, as I said, it is less limited in terms of the array that we can use it with, and we can also design the beamformer to enhance or attenuate some signals from different directions. So let's keep on talking a little more about specific applications that could use this approach. So the first one would be for wearable arrays, where, for instance, we have participated in some kind of an acoustic environment, and we have captured this acoustic environment in order to re-experience this sometime later, similar that when we do with videos, for example. We can also maybe share this experience in some platforms that may support this kind of a format. And another different application would be for assisted listening, where we have a very noisy environment and we would like to focus on our attention on some kind of source, maybe a speaker, or maybe attenuate other noise from different directions. And for other devices, such as mobile devices, we can use such an approach in teleconferencing, for example, or basically any other entertainment based application which uses binaural signals. Okay, so from here, let's go talk about some literature review in this topic. In here, I have a list of some works, some examples for works that use this method to generate binaural signals. And if we would go over and read a lot of the recent works, we will still be left with a lot of question marks regarding how exactly do we design such a system. So I have the equation that basically tells us most of the parameters we need for the design, but if we would go over the works, it would still not be clear how exactly we need to choose the number of beamformers, the scaling factors, the steering directions themselves, and also the beamformer type. And maybe more importantly is that it is still not clear how each of these parameters actually affects the quality of the reproduced sound. So let's continue a little bit with the literature review, where I'll be presenting a summary of recent work to try to answer some of those questions that I just stated. So I've listed the questions in this table, and the work that I'm talking about is listed here. So basically in this work, they divided their analysis to two types of arrays, for spherical arrays and for more general arrays. And for spherical arrays, they have showed some conditions that help us to design the system. And let's go over them very briefly. So as they showed, if we would use a spherical array with a spherical harmonic order of NA, which is the spherical harmonics of the sound field, and we would use maximum directivity beamformers, and we will choose the steering directions to correspond to a sampling scheme on the sphere, which is aliasing free up to a spherical harmonic order of ND, which is the maximum between the spherical harmonic order of the HRTFs and of the sound field. Then if these three conditions are met, then our design of the beamforming-based system that produces the binaural signals, which is this BFBR here, it would be equivalent to performing the plane wave decomposition, which means that we will get the ambisonic signal at the output. So this actually answers a lot of the questions that I've written below, because it tells us exactly how to design the system, and also we have a very good understanding about the quality of the reproduced sound, because we would get the ambisonic signal at the output, which is very well studied. So this is the case for the spherical array, and for more general arrays, the analysis tries to answer or give some guideline on how do we choose the number of directions when we use general arrays. And in this case, what they've shown is that we can use the directivity factor of the maximum directivity beamformer in order to know how many directions we will probably need in order to get a high quality reproduction. And what they have shown is that this number of beamformers, of maximum directivity beamformers specifically, should be very similar to the average directivity factor, where the averaging is performed over all directions. Now, this may be a function of frequency. And yeah, so at least for the maximum directivity beamformer, when used with general arrays, we have some idea on how do we exactly need to choose the number of directions or number of beamformers. But for all of the other questions, this is still not clear. General arrays are maybe more complex in order to understand carefully how do we need to choose all of these parameters and how exactly this will affect the reproduced sound. So what we try to do, which is what I'll be presenting now, is to take on a different approach, where the aim is to extend this framework, so get a very well theoretical framework to how to design such a system, or any system, to produce binaural reproduction, where the aim is to focus on general arrays. Meaning that they don't have to be spherical. For example, this could be very relevant for wearable arrays, and our directional resolution may be very limited, such that we are not expecting to get a higher order ambisonic signal, since it's not possible with such small arrays. And our approach is to estimate the binaural signals directly from the microphones. And we will do that by assuming that the sound field is comprised of capital D different sources, which are independent from one another and identically distributed. So this may seem like a limitation at first. However, it can be shown that if we would get an binaural signal with very low error with very low estimation error, then this could be the same approach can be used with a lot of different sound fields. So it's not really a limitation. However, the exact derivation of the proof is left out of the scope of this paper. Okay, so let's now see the proposed method. First, I'll present some of the models that we used in order to develop the method. So what I have here on the left is the array measurements, or the model that we used for the array measurements. V here is the steering matrix between each of the sources to the microphones. The vector S here holds the amplitudes or the signals for each of the D sources. And I will also be using the signal power and noise power denoted by sigma S squared and sigma N squared, respectively. But we don't really need to estimate them. This is just going to help us with the robustness of our approach. And on the right here, this would be the true model of the binaural signals, assuming that the sound field is indeed comprised of the different sources. So this is simply the inner product between the vector containing the HRTFs from the corresponding directions and the source of amplitude. So what we do first is we filter the microphone signals or perform linear estimation. The filter coefficients will be denoted C, and this will be performed for the left and right ears separately. And the output of this first block is simply the inner product between the filter and the microphone signals. I have also denoted this as P hat, meaning that this is going to be the estimated binaural signal, but this will only correspond to a really good binaural signal if we choose C carefully. So how will we choose C? We will first subtract the estimated binaural signal from the true model of the binaural signals, and we will find C. We will find C that minimizes the MSC of this expression. And if we will do that, we will get the following expression. So we can see here that, first of all, it could be easily extended to various HRTFs, since we just need to replace this vector of HRTFs with a different one. And it also supports head rotation by changing the steering matrix correspondingly. And in here you can see why I needed to know something about the signal power and noise power, but this is just to make this inversion more robust. However, if we will have this information, this could help the estimation, and also there are other methods for performing this regularization. Now, this is not a new formulation. Of course, it was proposed before, and specifically for binaural reproduction. However, usually it is studied in the context of sound field control. And when it was studied with estimating binaural signals, it was usually studied with spherical microphone arrays. So once again, we have focused here on more general arrays, which may be limited in resolution. So let's now see briefly some performance measures for this proposed method. And what we see here is the normalized error of the binaural signal. If we will plug in the expressions from the previous slide, we will get the following expression. So we have some kind of a weighting here between these two terms. Now, next, let's assume that the SNR is sufficiently large such that we can neglect this part here. And we will be left with this expression. This sigma S squared cancels out, and we are left with this expression. And as we can see, if the SNR is high, we don't have a lot of influence on the about the signal and the noise powers. And what we can see from here is that basically this filter C is trying to do some kind of a matching between the steering vectors and the HRTFs. So this could be also thought of as the error of estimating the HRTFs from the array steering vectors. And that's one of the reasons why we call this error as a matching of the binaural signals. Okay, so let's go over some simulation results. I'll begin by presenting a simulation we did with the spherical array. And in this case, I simulated a rigid spherical array with 32 microphones with 4.2 centimeters radius. And the SNR that we assumed in order to calculate the coefficient is 20 dB. And in here I studied the K100 dummy head for the HRTFs. Now the source directions were nearly uniform in spiral scheme with different number of sources. We will see that on the next slide. And what we will be studying is the error of the reproduction. So we see here this normalized error as a function of frequency, and the scale is in dB. And because it is a normalized error, then 0 dB is a very large error, but minus 15 and minus 20 dB and below is very small error. And what we see here is the error for the case when the acoustic environment is comprised of 240 sources. And we see that there is a So we see that at the lower frequency range, at approximately below 2 kilohertz, there is a very small error. But at the higher frequencies, there is a very large error. And the next thing that we can study is what this error will be if the environment was less complex and it would be comprised of less sources. So looking at the same error plot, but when the number of sources is decreasing, for 32 in this example, we see that the error is decreasing at the higher frequencies. And also when we decrease it further to 20 sources or only 6 sources, we see that we have a very accurate estimation in the entire frequency range. Now what we can do here is basically maybe think about a way to estimate the binaural signals with different filters depending on frequency. So at the lower frequencies, we can get a very accurate estimation for very complex sound fields. So we will use the filters that correspond to a lot of the sound sources. And as the frequency increase, we will maybe need to choose a sparser direction grid when we calculate the filters. So this means that it will not be able to reproduce more complex sound fields, but this is expected to be somewhat limited at higher frequencies. Now, I said that we are very interested in general arrays, so let's see the case of a much more compact and simple array comprised of only 6 microphones arranged in this semicircular geometry. And in here, it was mounted on a spherical array just to represent some kind of a wearable array, for example. And other than the array, all of the other parameters are similar to the previous simulation. So the same SNR was used, assumed the same HRTFs, and source directions. So looking at the same error, and once again, for the case of the complex acoustic environments with 240 sources, we once again receive a relatively low errors at the lower frequency range, this time smaller than 1.5 kilohertz. And we see that as the frequency increase, as expected, we get higher errors. But if once again we will study what happens when the environment is less complex, containing much less sources like 32 or 20, we don't see a lot of change. So there is still very large errors in these cases, which makes sense because this array is much more, it is much more simple, and its resolution is much more limited than the spherical array. However, if we will keep on decreasing the number of sources to 6 sources, we are starting to get lower errors. And once again, maybe we will use with this array sparser directions grid. So this is starting to look like the beamforming-based approach, where we have just a very small maybe set of directions where we are trying to reproduce sound field from, or at least at the higher frequencies. Okay, so to conclude, we saw that for the beamforming-based approach, we have a very developed theoretical framework for spherical arrays, but with other types of arrays, it is much more limited. So our proposed method was to directly minimize the binaural signal error, and we indeed got a relatively small error at a limited frequency range. But this method supports head rotation. It could be easily extended to different HRTFs. Now, it was not shown here, but it is still work in progress. We have some listening tests, and we are getting relatively promising reproduction with high quality, even with a much smaller array. Now, for future work, except of performing the listening test more formally, we will also like to develop the theoretical framework further and get an accurate conditions to when the estimation can be exact with general arrays, and also to develop a method that could give us some guideline on how to choose the number of sources that we assume in order to calculate the filters, which will probably depend on frequency, as we saw. and of course study the performance with more HRTF databases. So that was all. Thank you very much for listening.
All right, thanks a lot for your talk. Thank you, very interesting. Do we have any questions from the audience?
See a raise your hand button on the right side of your screen if you'd like to ask questions.
No questions?
We have one.
Okay.
Nick, go ahead and ask.
Okay, hi. Thank you for your presentation. I'm a student at Penn State, so not a professional expert. And so I just wanted to ask something for my clarification and understanding, if that, since there's no other questions.
Yeah, sure.
So with this approach, then, it sounds similar to kind of a spherical harmonic ambisonics-based approach, but with a different kind of weighting matrix that is more general. So would you consider the ambisonics approach kind of like a subset of this more broad theory, or is it distinct?
So I guess there are some conditions under which the two may be very similar to when we use maximum directivity beamformers, we may get ambisonic signal at the output. However, in this case, the aim was to study arrays where it will be very difficult but we are actually currently working on trying to develop the framework even further to have more exact exact conditions on when the estimation will be exact. And when it will be exact, it may be similar to the ambisonic. So there will be some conditions where the two are similar, but I think that in terms of the design of the system, it will be a different approach, because it will also enable to give something, at least with low error, when you can't really have any accurate estimation of the ambisonic signal. I hope this answers your question somehow.
Yeah, no, that perfect. Thank you.
Are there any further questions?
There is one from Ayrton. Go ahead and ask your question.
Okay, thank you for the talk. I'm also a student. I would like to ask about this filter coefficients that you are using. Are you considering also maybe adaptive filtering on further on another maybe another study? And if so, which type of adaptive filtering are you considering?
Okay, so this is good questions. If we will go back looking at the expression for the filters, I will explain what we are currently working on, but this could very well be extended to some of the things that you have proposed. So basically, what we see in this term is the assumption of the sound fields, which are independent from one another. However, if we will have some information or a way to estimate the covariance matrix of the signal and the noise, then we can plug it in this instead of this matrix here, and then maybe get a better estimation when we have this information. However, this is something for future work, because currently we want to show that even if we do this assumption that that the sources are uncorrelated, basically, then we can still have a very accurate estimation, even if the sound field is different. And we have started to get some results. We see the conditions, and maybe when these conditions are not met, then we can do something similar to what you proposed, using an adaptive estimation of the covariance matrices of the signal and the noise. And this could very well improve the performance in this case. Yeah. Thank you for the question.
Thank you very much.
Okay, thank you. Thank you for your talk. Thank you for your answers. Let's give another round of applause, and then we should move on to the next speaker.
Thank you very much.
Go, Dustin. Okay, great. Thank you.
I'm ready to go. Yeah.
All right, then let's go. The next speaker is Matan Ben Asher, and he is from Waves in Israel, I guess. And he will be giving a talk called Virtual Reality Music in the Real World. And he will address certain issues about head tracking and rotation with respect to train movements and things like that. I'm looking forward to it. Let's go.
Right. Hello, everyone. I'm Matan from Waves. And I'll be presenting the paper Virtual Reality Music in the Real World. I'll start by saying that the real world was a very different place when we wrote this paper, obviously, but it's still highly relevant, as you'll see in the items. A lot of the stuff is relevant.
Matan,
paper discusses.
sorry,
Yes.
Matan, excuse me, sorry.
Yeah.
I think you're amplified. Are you? If you select
Yes.
that
Now I am.
those tools. Okay. Yeah.
Now
And then
I'm
also,
amplified.
it
Now
might
better?
be an issue. It might be an issue of your microphone. I think when you're turning your
Okay.
head away from the microphone, we're losing you a little bit. But otherwise, sounds great. Thank you.
All right. Yeah, so I'm with the Quest. Now amplified. So the paper will be the paper discusses an issue that was not discussed so far. We're not going to be talking about audio processing at all. We're going to be talking about the pre-processing aspects of head tracking when you want to use it and when you want to apply it to binaural audio. And as most of you are familiar, this is a big deal. It's been happening for quite a while now. And let's just begin. How can I advance this slide here? Yeah. So binaural rendering with head tracking. So I won't elaborate too much on binaural rendering because we're on the third day in here and everybody was talking about it. But we do know that binaural rendering involves when we apply binaural cues, which are ITD and ILD and other binaural cues in order to present a virtual source in some location in space, in some fixed location in space. And we also know that head tracking is very important to this aspect because all of these cues and all of these filters that are applied, HRTFs that we discussed in this and other items that happens in the room reflections, the response of the room to where you are relative to other objects and other people, that all changes when you rotate your head, obviously, and when you move around. So this is what head tracking does. Head tracking in the first degree, what it attempts to do is position a source in a static relative to your head motion. And head tracking is typically can be done in 6 degrees of freedom. So we just talk about XYZ translation and also in yaw control. And you can also talk about, you can also describe orientation in quaternions and other forms. Moving on to the next slide, we'll see, and this actually combines with what was talked about before in the previous talks about the list of the creator's intent versus what the listener is hearing. So when we're talking about music and also film, this most of this content is all created in studios, either in studios that have a surround system or stereo speakers, and they're all being done by these mixing engineers and the artists while sitting in a sweet spot and listening to a real studio speakers. So when we consume content that is stereo 5.1, 7.1, and all of this content, we need to keep in mind that this content was created in some kind of an environment, and that is the intent of the artist was projected into this environment. And so then when we recreate binaural audio, and this is what we did with our first product with NX with the Pro Audio plugin, we ideally want to create a set of virtual loudspeakers which are similar to where this content was created. The virtual loudspeakers will emulate loudspeakers in the mix room using binaural rendering, and this helps both the studio engineers but also on the consumer side. The studio engineers in our first product were using this NX to do their mixing when they're not in the studio. So they needed to have a virtual sort of studio when they were working from home, as we all do right now, or a lot of us do right now, and or on the go. And it would still simulate that same feel of the studio where the speakers are in that position and mix like that. But in the consumer space, it's also very similar because you know that the engineer was when he was creating this content, you want to reproduce the same environment. So this is the ideal listening or in the intended listening environment when we're talking about the existing formats of audio for film and for music as well. Now the way we do it, and it's similar to other technologies, we actually use parametric HRTF simulation. This allows us, instead of measuring HRTFs, this allows us to actually optimize, to personalize HRTFs to some degree of the user's dimensions, and we simulate these virtual loudspeakers. But we also need to add the room simulation, and the room simulation is a big deal because you need to decide which room you want to simulate this user. Do you want to simulate the room that he or she are in, or do you want to simulate the studio or the studio that was created in, or do you want to create some optimal environment? And we did some of this and some of that. In the first product, it was this optimal space, and in the Abbey Road Studio product, it was simulating the actual Abbey Road Studio 3. Now, in the case of head tracking, you can do with either IMUs or cameras, and some of you are familiar with these items. And also, you know, when you're wearing a headset, so obviously head tracking is happening with a lot of sensors. But it can be with 6 degrees of freedom or 3 degrees of freedom, and you can do a combination of tracking, so you can increase the rate of the tracker. These are all things that affect the experience very strongly, especially with audio, even more than with visuals. And that was it for the product where we were talking about the mixing room, or for the professionals. We were talking about simulating a room and the speakers, and we were also doing head tracking. Now let's pause here and ask ourselves the question: when you do head tracking, and if anyone has ever attempted to do this kind of technology before, you realize very quickly that that head tracking means you're getting a degree of the head or an orientation of the head, and you want to virtualize a source relative to that head. But when you're getting the orientation of the head, it's relative to some reference. It's relative to some, usually a static reference. It's whether the IMU, when you turned it on, where it was pointing, or is it magnetic north, or if it's a camera, it's usually where the camera is facing. But anyway, when you're getting head tracking information or tracking information, it's relative to a reference. And when you virtualize a sound source, and you're in the real world, you're looking outside and you're seeing physical objects, you're not in a VR environment, you're in the real world, you're trying to virtualize a sound source in a physical place, in a real physical place, a virtual source, like an augmented reality. So you're usually doing this, and you have to decide where your forward is in the real world, where your forward is, and place all the objects relative to that, relative to that forward. Now, in the studio product, this is not a problem, because the studio engineer, when they're doing a mix, they're sitting down and they're attempting to mix, and they decide, okay, my speakers need to be here in the forward. Now I fix them here. I press calibrate. We have like a button, a sweet spot, and now they're here for the rest of the session, and that's good enough. I don't need them to move around when I'm doing the mix. Or even better, some of them even use this a little, even to some extent. They move to like a keyboard if they have like a piano or something next to them, and they're playing the MIDI keyboard, and rather than the speaker still coming from that direction, from the front, they can recalibrate and have the speakers have them facing in front of them. So this is like a manual sort of way of positioning speakers. And so as long as you're static, this is all great. But what happens when you're in motion? What happens when you want to render a binaural of 5.1, 7.1, or just stereo, and the listener is outside, is in a train is moving around the car, or riding a bicycle, and or walking around in the street. Now, what happens if I fix the source to a static position? Then the speakers will be in front of me as long as I'm moving in the same direction that I was moving. But then when I turn a street corner, the speakers will be on the side because there's head tracking, and so the head tracking keeps them constant here. And now I'm walking in another direction, and I have my speakers stuck on my side, and I don't want this kind of behavior, probably, and that's only one example. There's tons of examples where this becomes a problem. You have a train riding, and the train is slowly shifting to the left, or slowly shifting to the right. If you have head tracking with an IMU and you're not recalibrating your reference, then it's going to be causing the speakers to sort of drift around, move around you, because the head tracker does not know if it's your head motion that you want to do head tracking relative to, or the reference is changing. So and we realized quite quickly that we need to decide what to do here. And this is not a technical problem as much as it is a UX sort of decision problem. Because if you think about it, this kind of technology had never, not technology, but this kind of experience had never existed before. If we had experiences in a living room, and in a studio or in a movie theater, then we were static, and the speakers were static, and we had these speakers externalized, and we weren't moving around, and it didn't really matter. And if you wore headphones, it was, the classic kind of headphones that we still see around for most people, are the lateralization. They're all in your head, so there's no directionality at all anyway. So if there's no directionality, then it doesn't matter which way I'm facing. They're all moving around with. But if you want to have binaural audio with head tracking, so you want to have this externalization effect. That means that you're creating some augmented reality that's moving around with you in the world, and this augmented reality is a sound source. So it's not some like here, like we have in VR. There's not some icon that's sort of tracking you and you can press it. It's your music. It's your audio. You don't want it to move when it's not supposed to move, and you need to really ask yourself, what do you want to happen when you're actually listening to music or consuming a film that is going to be pleasing and it's going to be comfortable. So this is the first problem, obviously, that we understood that we needed to do was to distinguish between the head motion. When I mean head motion, I mean there's a head tracker and I'm moving my head from side to side. And I want to do the audio, which all of you probably know, with the head tracking, where you have the sources fixed. But when you move your whole body, the head sensor is also detecting this rotation, and in that case, you don't want to do that, or you maybe want to do it for a while, and then you want to move it here because you're facing in another direction. And there's combinations of events and use cases that when you think about it, it creates a big problem. So you need to, first thing you need to do is distinguish them. And that is the first thing that we did, is we decided, okay, to distinguish between head movements and reference movement, okay, let's just add another sensor. So we added another sensor, meaning we used the sensor on the phone, and we did it in our mobile apps that we first published. So we used the IMU within the phone and the IMU in the sensor, and together they work to make the decision. Now, okay, this is just the hardware aspect of it, which sensor I'm using, but what do I do with this second sensor? How do I use it in order to make the experience smooth? And this came a lot of thinking and experience with actually the first products of NX, when we did the NX for the virtual studio, and the responses that we got from the studio engineers. And the responses that we got from the studio engineers were originally, before moving reference, before this problem even existed, were why are you even doing head tracking? Why are you guys doing this to us? We have waves, we have hundreds of thousands of studio engineers using this technology, some of them doing it for decades, and using headphones for decades. And they asked us, well, why are you giving us this strange kind of thing that's sort of feeling like the speakers are moving around? And we told them, okay, but this is how you experience sound in the real world. This is how your studio sounds like. And they said, okay, but I want to be in the sweet spot all the time. I want to be in the sweet spot all the time. Now, what does that mean? When they sit in the studio, they said they sit very still, and they try not to move their head at all, because they're aware that if they move around, then the mix changes, and they're aware that if they move around, then the whole scene, the whole spatial scene changes. So they said, okay, well, we sit still, we don't want to do that. But we know, and we know this from research, that these even the minor head movements are what convince you that the sound is even coming from outside and not from within you, because your mind is expecting them to move when you're moving. And this is part of what we're adding. We added the head tracking for. And that was one step. But from that understanding, we realized that when you're consuming content, and you're doing it for the fun of it or for whatever reason, you're consuming audio content, you're expecting it to come from some front. Now, this front is, as we know, it can't be the front attached to your head, right? It can't be headlocked, because if it's headlocked, we know that the sound will not be externalized properly, and it's not real, and then there's listener fatigue and so on. But on the other hand, it can't be a headlock. But then, what is this front? Where is this front? Is it where my body is facing? It's not necessarily. When maybe I'm sitting in a train, and the train is going that way, but I'm sitting on the side of, like, a subway. I'm sitting on the side of the subway, and the front is still not where my body is facing. It's where my motion is moving. So we thought, maybe let's detect the direction of where you're moving all the time, and then put the front there. But then we realized even more that there's a much simpler solution that makes more sense from a UX point of view, from a user experience point of view. And that is, if you want if you want the sound to come from the front, and vice versa, you usually look to where the sound comes from. If you're experiencing this sound, that is the ideal positioning place. Then why not have the sound sort of follow you to the front, and see to it that most of the time the sound will be in front of you, so that when you're demoing binaural head tracking, you usually like to do that and show that the sound is coming from behind you, because it's a very cool effect. But eventually, you don't want to listen to music from that direction, or at least not all the time. Maybe you want moving sources and stuff like that. But if you're listening to stereo music, you don't put it there. Nobody sits in there purposely in their office or somewhere and put their stereo speakers to the side of them. They put them in front of them, and the same way for when riding a car and so on. And what is that front? That front is the average look direction of the head. It's the average look direction of the head, and it can be a long average, and it can be a short average. But the average look direction of the head, like I'm facing you guys in the audience, I'm looking to some point, and there is an average, and the sound should come from that place. So we realized that, and that you can do with one sensor. So you have the moving, the reference following where the head is all the time. Now, what do you do with this second sensor? What do I do when I take a sharp turn right towards the screen, or something like this, or walk in another direction without crashing into my wall here? The second sensor, what we decided to do with this, you can get information from that second sensor, from the statistics of that second sensor, that the direction of motion has changed. And you don't care where that direction of motion is. As long as you can get the information of that second sensor, whether it's in your backpack or in your pocket, or you're holding it in your hand and you're wiggling your hand around, you can get information if that pattern is changed. And usually when people are in motion, they have a pattern. That pattern should be static. Whether it's a pattern when you could be running or cycling, but there's still a pattern, or riding a train. And when there's a change in direction, that pattern changes. And when that pattern changes, those are the points where you want to start moving the reference, recalibrating, so to speak. And this is what we did. So in this diagram, you can see the head sensor, and you can see the second sensor at the bottom. The second sensor is doing some sort of like a classification or a regressor, that all it needs to do is tell us how much do we need to move right now? How much do we need to calibrate that head sensor? Now, if you're static, there's nothing at all. It'll just output 0. You don't care. The phone is on the table, and you're in a static environment. There's no reason to move the sensor at all. The reference should be static, and you use only the head sensor. But if that changes, then this second sensor will tell the first sensor, okay, now you need to start calibrating yourself. What does it mean? You need to move your reference. But where do we move the reference? This is important. We always move it to the same direction. We move it towards where your head is, where your average head is. So if we move it very slowly, we move it very slowly towards the head. If we move it very quickly, like in 0 time, we can move it towards the head. That means it'll just be in front of you immediately. And for that split second or several seconds, it could be no tracking at all in that case. So maybe I wiggle around and I'm moving and I'm doing this sort of breakdance motion while doing binaural audio with head tracking. The best thing to do in that case is not do any head tracking, because it'll just be a very unpleasant experience. But then when my motion is sort of it stabilizes, then you can release the head tracking again. The amount will go down, the reference will be released, and it will be stuck in place, and you'll go back to normal head tracking. And this is what we did. There's a diagram here explaining how this is done, how this takes place. So you can see at the top diagram, you can see that the bold line is wiggling from side to side. That's the head, and then there's the dotted line is the reference, and you can see the reference is always sort of in the middle of the thing. And then at the bottom graph, you see the user walking, and the user taking at let's say go back to like T5, go all the way to T5. The user is taking suddenly a sharp turn left, and when that happens, you can see the amount in the third graph is jumping up. And that causes the dotted line at the top graph. You can see the dotted line at the top graph. It causes it to sort of follow very tightly the dark graph. That means that the reference is now moving along with the head. It's just, again, it's like headlocked in that case, until there's a stabilization. The user again is walking in a straight line, and when it stabilizes, the reference also is released from the head. And you can see at the top graph that the dotted line is suddenly now in a new position, but it's always in some sort of average from the head sensor. And this is with dual sensor, and we also have a similar thing with two sensors, with one sensor. There, I'm not going to elaborate long because I think we don't have a lot of time, and I do want to leave time for questions. But to be very short, you can extract the same information. It's a little more difficult, but you can extract the same information from a single sensor, where you need to sort of distinguish, is this normal head motion, or is this motion something that is different from just rotating your head from side to side? Is the reference changing? And then you extract the amount in the same sort of classification approach, and using that amount, you calibrate. Where do you calibrate to? You calibrate, the amount is only the speed in which you calibrate, but you always calibrate to the same direction, which is the forward direction of the head. Now, there's a demo showing this right now. I'll play the video before I'll just explain what you're going to be seeing in the video, because I don't think I can talk during the video. You'll see me walking around in an environment and outside, taking turns, and the audio is irrelevant completely. There's not going to be binaural audio or any spatialization in the audio. The audio is only to explain what's happening right now. And you'll see me rotating my head from side to side, and you'll also see me moving around, and there's also a section in the car. What you want to follow is on the top left corner. You'll see the iPhone app that's used for this, the mobile app that's used for this, and you see the head. And the head, when my reference is static, when I'm rotating my head from side to side, you'll see the head moving from side to side. But then when I turn my body, you'll see that the head is quickly adjusting, and it's recalibrating, or it's sort of going to the center forward And then after I stabilize my motion, you'll see again that I can move my head from side to side, and again it's doing the head tracking. So follow the head on the left and compare it to what my body is doing in the movie that we're going to show. And next slide. Okay, picking up headphones, putting them on the head, and shake the phone, and look to the left, look to the right, look to the left, look to the right. Now getting up while the phone is still on table, and 300-degree turn. No moving reference because the phone is on table. Looking to the left, looking to the right. Picking up the phone and walking towards the path. And taking a sharp right turn. And then walking in a straight line. Looking to the right. Looking to the left. Looking to the right. Looking to the left. Looking to the right. Looking to the left. You can see the phone is still in my hand, and as soon as I'm going to put it in my pocket. Looking to the left. Now taking a sharp right turn around the tree, and again looking to the left, looking to the right, looking to the left, looking to the right. Now putting my phone in my pocket. Looking to the right, looking to the left, to the right, taking a sharp turn right, looking to the right, looking to the left, looking to the right, looking to the left, and I'll start jogging. Jogging a little bit, looking to the right, looking to the left, looking to the right, and sitting down to rest. Looking to the right, looking to the left, and getting up, walking towards the table. Looking to the right, looking to the left, right, and that's it. Now shooting in the car. Driving in reverse. Not me driving, I'm just sitting next to the driver. Cars turning to the right. To the right, to the left. Yep. And that's it. Yep, that's about it. I think we have time a little bit for questions. Yeah, if you have. Did everyone see the movie? Because I on the big screen I didn't see it. I only saw it in the browser, but I think nobody was giving frowning faces. So yeah.
I could see it. It was nice to see your real life appearance in the movie. Is there maybe one question from the audience? We probably have time for that.
All right.
Doesn't seem like it.
if you have a question.
No?
All right, guess not.
Maybe one quick question from me. So does this dual sensor, these dual sensor applications also help with IMU drift? And is that still an issue?
Yeah, of course. Yeah, on the way, it also solves the IMU drift because IMU drift is not a problem anymore once you understand that this is what you want to do anyway. So you don't, if you're not doing a static environment and you're in mobile environment, so you want to move the reference. You want to center it most of the time anyway, as long as your IMU drift is not crazy, right? I mean, if it's a very, very bad IMU drift, then it won't solve. But if it's, if it's minor, then this solves that problem on the way.
That seems like a great advantage.
One quick question from Chris Travis. Go ahead.
Thanks. Yeah, I just wanted to ask. That's fascinating and great to see. Thank you very much. It looks really important. My question is, does that basically solve this problem? Are you comfortable that you've kind of approaching a solution that's nice and contained and job done?
Oh, I'm sorry. I'm not sure I heard the entire question. I think you're asking if we think this solution is working good enough for us.
Yeah. Are
Yeah.
you happy?
So yeah, definitely. Yeah. So definitely the second sensor, the dual sensor algorithm. We released it several years ago in the phone apps, and it's gotten very positive responses from many users. It's much better than other solutions that I've seen that sort of follow you around all the time. There's solutions that I've seen that they follow you around and that that solves the problem, but it's an overkill and it's very disorienting in many cases. You don't want that to happen. You want it to be static. And yeah, it's a very robust solution. We've gotten very good remarks on it. It solves many different cases without any difference in the algorithm, without any settings. So it solves the case of boarding a train and also riding a bicycle. It's a very different situation. Imagine walking down the street and tying your shoelace, or walking with the dog. It's pulling you from side to side. All these cases, when you're doing binaural head tracking in and out, I don't know how many people have experienced this outside when they're walking outside. It's a problem. It's something that you need to think about from a user experience point of view. And this totally solves it. We have people who've been using it for several years now, and they love it.
Great.
Okay, thanks a lot. Let's give another one of these. Okay. I guess we can move on to the next speaker. Thank you.
All right.
Everything all right?
Yeah, can you hear me?
I can.
Perfect.
Oh, don't worry about the microphone. Okay, I guess we're good to go.
Sorry, I just have trouble to launching my slides.
Okay.
Okay, is Tristan on the stage or in the room? Niels, do you see Tristan?
He's on stage, yes.
Yes, okay. I have to ask Tristan if you could go on air, on your host tools and the on air button.
Yep.
Okay, I'm still not seeing.
Okay,
There he
can
is.
you hear me?
Okay, yes, now I see you. And then also the amplify voice button on the same host tools.
Yep.
Yep, great.
Can you see my slides though? Because I don't see them
Yes.
on the screen. Yeah? Okay, perfect.
Great. I guess
Okay,
then we
so
can start.
hello everyone. Yep. So my name is Tristan, and I'm going to talk about a study on the adaptation to new auditory localization cues, and I'll be presenting our current advances on a new step to optimize sound localization adaptation with vision. So I want to. Can you see my slide changing? Because I cannot.
No, we don't see it changing. At least I don't. I think a few people are not seeing it change.
Okay, it should be good now, right? Yeah. Okay.
Yeah.
Sorry about that. So, so the AVAR-related transfer functions are used today for binaural synthesis to reproduce auditory spatialized scenes. And so the HRTFs, they contain the transformations that our body applies to sounds and are thus deeply linked to morphological characteristics. And therefore, HRTF are individual, and they need to be actually. Sorry, sorry about that. I cannot access my slide. Okay, good. And so they need to be individual when used, which actually requires special equipment and is very consuming in time. So because of that, today, in practical situation, most of the time, HRTFs are used as non-individual HRTF, either generic or measured from someone else's ears. Unfortunately, some specialization with non-individual HRTF leads to unpredictable distortion of the auditory localization. We observe more front-back confusion and more errors in the precision of the localization. Luckily, our auditory system has the ability to adapt to new HRTF. And indeed, numerous studies have observed that with time and or training, we can improve our auditory localization performance with non-individual HRTF. So this manifests with a decrease in front-back confusions, a decrease of the angular errors made in localization tests, and some studies have shown that some of the improvement can be even retained for up to 4 months after only 2 sessions of training. And even more interestingly, the improvements that are made in anechoic environments and with the training using white noises stimuli can generalize to untrained positions, different sounds such as the voice, and as well as in reverberant environments. So a great number of training have been used to foster such adaptation. So the most simple one is just to expose the participants to sound sources specialized with new HRTF. So although it takes time, it can lead actually to a significant improvement of the localization performance. More specific training have also been proposed where feedbacks are given on the position of the sound sources to increase the speed of the training. But the most effective training method that have been proposed are the ones involving an active participation in training tasks. Indeed, this training, such training have been shown to create significant adaptation in down to 3 sessions in 3 days. And for example, the kind of numbers that we can find is like, so some groups used in the study of porcelain cats, so we measured 25% of front-back confusions in a localization test before the adaptation, and after 3 sessions, only 11% of front-back confusion were measured. And these 11% are actually comparable to the ratios measured for the control group using individual HRTF before training. So these active trainings are interesting for their results, obviously, but also because they use multisensory feedbacks and an active participation in an exploratory task. And both of these factors have been shown to be beneficial to the memorization of the localization of visual objects. So these programs actually can lead to a fast and significant improvement of the auditory localization performance using either vision or proprioception in addition to vision, or to audition, but never both together. So although the ability to adapt has been shown, we also observed that it exists a very strong inter-individual differences in the capacity to adapt. And while some participants indeed improve significantly their performance, some others just do not improve during the sessions. And so one of the possibilities is that part of that explanation is linked to the efficiency of the training tasks that are used. So in that sense, investigating ways to improve the training tasks that are currently used would possibly reduce this phenomenon, and at least it will benefit to the participants that are already improving. So we got interested in this training and improving this training. And as I said before, all of this training are bimodal, so they either use vision or proprioception, but never both together. And indeed, it's been shown that vision is not necessary in such training, but still it remains our most precise modality when it comes to spatial localization. And there is many examples of interactions between audition and vision, and even when it comes to auditory localization. For example, the absence of landmarks actually deteriorates the localization performance. So what we wanted to see with the study was if a trimodal version of the training would actually lead to a better improvement than a bimodal version. And so in other words, can vision improve the effect of an audio proprioceptive training task? So now I'll explain these experimental designs that we aim to use. This design is inspired by the study of person and cats of 2012. So the whole experiment was actually will be actually carried out in a virtual environment using an HMD and a Vive controller for the pointing methods. So briefly, so this is the general procedure that we use. So before actually the training takes place, participants they carry out an HRTF selection, which allows us to select a specific HRTF. So this was designed so that the groups actually are kind of homogenic, because in other studies we noticed that if you don't do this task, you will have a very, very strong inter-individual differences at the start of the experiment, and this will complicate the analysis later of the results. So then, after this selection, the participants, they carry out a first test of localization that allows us to have a ground measure of their performance with the non-individual HRTF. And then, for 3 consecutive days, they participate in a quick training task, and then another localization test aimed to assess the new performance. So in order to measure the retainment of the improvement, 1 week after the last session, we will do another localization test in order to assess the performance 1 week after. So to study our hypothesis, so we create 3 groups that actually are separated by the 3 different training tasks that I used. So the first group is very similar to the one that were proposed by person and cats, in the way that they participate in a bimodal adaptation task. So they will be given feedbacks in auditory and proprioceptive modalities. And then another group will do the same task, but with the addition of vision. And so this will allow us to evaluate the influence of vision on this bimodal task. And then our third group will be our control group, where the participant will actually, which is actually different than the other studies, they will actually participate in the training, but they will not have any specialized information. In that way, so their auditory system will not be given any information to adapt. And so the adaptation to HRTF should be impossible with the training. But still, the interest of that group is that it will allow us to measure all the improvements that are not connected to the adaptation to HRTF. In other words, it's the improvements that are linked to the familiarization with the procedure and the equipment. So now I will explain to you the different tasks that we use. So the first one is so an HRTF selection that allows us to choose the HRTF that each participant is going to use. And this one is inspired by a task proposed by Andropoulou and Katz. So the participant will actually have to estimate the realism of trajectories that are previously described to them on a Likert scale. This will allow us to have a score of the realism of each trajectories. So 3 trajectories are to be tested. And so in the first in the study that was proposed by Andropoulou and Katz, they only proposed 2 trajectories. But as you will see later, as we test only the frontal hemisphere, we added a third trajectory to further to have more information about the localization in that hemisphere. So 7 HRTF pairs are tested during this task. And after this task, so we choose the best HRTF for each participant, which is we do an average of the score, which gives us the best, in quotation, HRTF for them. Also imperfect, this technique allows us to make sure that we do not choose the worst HRTF, and this allows us to reduce the inter-individual differences at the start of the experiment. So to assess the performance of the participants, we use a localization test composed of 2 blocks of 33 stimuli, all in the frontal hemisphere. So the stimuli that we use is a train of 3 40 ms wide nose bursts. And the pointing method that we use in this experiment is manual pointing. So this pointing has been shown to be robust and maybe the most stable pointing method between pointing methods such as the heads, for example, as the head pointing. So then the adaptation task is kind of the core of this study. So the training session is a 12-minute mini game of active exploration, and the task of the participant is to explore space to find inner targets in their frontal hemisphere. So to do so, they are given a feedback, an auditory feedback, that is actually a white and pink noise alternation. And this alternation is spatialized at the controller position in the palm of the hand. And the speed of the alternation varies with the target to controller angular distance. And this allows for a proprioceptive and auditory coupling that actually, as shown by Parson and Katz, allows for the adaptation to the HRTF. So, so as I said, we have 3 different groups, and so the first group is the one participating in the bimodal version of our training, where the sound is specialized and was given proprioceptive information in addition to the auditory ones. Then our second group is the one receiving the trimodal version with the addition of visual information. Indeed, the controller is for this group, the controller is rendered as a sphere in the virtual environment. And to make sure that the integration is made between the auditory information and the visual information, we had to make sure that the visual information actually helps the participants in the task. In that way, the color of the sphere actually changes relative to the target to controller distance. And as it is a bit like a cold and hot and cold game, it goes from blue for when it is far of the target, and red when the participant is close to the target. In addition to that, we apply a glow effect to the sphere that is synchronized with the white ping and noises interlination. And because it's been shown that this synchronization of visual information and auditory information actually helps for the integration of both of these modalities, and it also lowers the attentional effort that is needed. And then, as I said before, the control group will do the same task, but with non-specialized auditory information. So the measures that we collect during this in this study are the ones that we measure during the localization test, and they are measured in azimuth and elevation. But because we are dealing with a non-individual HRTF, we expect to have a lot of front-back confusions, will kind of parasite our data. And so we need a way to actually determine the error types of the measurements. And so to do that, we actually make a conversion from a spherical, that is azimuth and elevation coordinates, to interaural coordinates, that is lateral angle and polar angle. And so the data that we are actually applying our statistical analysis on are the lateral and polar angle errors, and the error types that is determined thanks to the polar angles, especially for the front-back confusion. So unfortunately, we couldn't yet test our hypothesis because of the COVID outbreak. And hopefully in September, we'll be able to work with participants if the universities in French opens again. But thanks to the literature, we can actually make some predictions. So what we expect is that both the bimodal and the trimodal training task will lead to adaptation. And what we expect to observe is a decrease in polar angle and lateral angle errors throughout these sessions, especially when we compare the first session to the one coming after the third training session. We also expect a decrease in front-back confusion, quite similar to the one, or hopefully stronger to the one observed with parcel and cats. And we also expect a greater adaptation with vision. So we expect that the improvement and the final performance of the trimodal group will be stronger than the one of the bimodal group. So now I'll discuss a few perspectives of this incoming results, and there will be another ways. The first one, it will be another way to optimize the training method that I use nowadays, and that will be with the implementation of game mechanics to further optimize the active training programs. So these have already been tested by Steinman et al. In 2019, but as said by the authors, new game mechanics should be explored to improve the attention of the participants and the engagement, and that should perhaps, there is good indication that it could actually improve the effect of such training. The last thing that I would like to discuss would be actually an application that that we expect to make with such program, and it's also the reason why we are interested in HRTF training programs. So the team I'm working with actually is working with post-stroke patients that are affected by unilateral spatial neglect. So this syndrome is actually manifest by a failure to attend to a side of space, and it is found in approximately 30% of the people after a post-stroke. And what we can see, so it greatly impacts everyday lives, and so practically what it is that these people are unable to take into account most of the time every information in the left side of the space. And so the most studied part of this is obviously visual, and this can lead to, for example, what we can see in the picture, where a whole side of the space is completely ignored, and it's not a perceptual effect, but really an attentional one. And recent studies have showed that the auditory localization is also affected, but very differently than the visual information. So the auditory localization is affected in a way that on the right side, it is actually quite close to the one of normal people, of non-affected people, with actually good performance from 0 facing the participant and 90 on the right. But then on the left side, what is often found is that every point on the left side is compressed around the point facing the patients. So what we want to explore is if such training that of rehabilitation of auditory space can lead actually these patients to rehabilitate their space and improve their ability to direct their attention on the left side. Thank you very much for your attention. And yeah, thank you.
Thanks a lot for your talk. Do we have any questions from the audience? The raise hand button has appeared. Doesn't seem like it. So it was interesting. AltSpace kicked me out during your talk, but it managed to be back in time. Maybe one question from me. So do you think that these processes can also work without directed tasks? So just from using these renderings together with visions?
Sorry, I didn't quite understand your question. Like,
so if we're using generic HRTFs in a scenario just as the one right now, will I also have a chance to learn it?
Well, it's quite possible because actually studies have shown like so some studies have just used ear molds to modify the HRTF and with no training. With no training whatsoever, and the participants, so they go through their everyday lives with the ear molds, and they actually adapt to these new HRTF. But it takes more time than with a specific training aimed to that. But of course, for example, if you're in AltSpace with an HMD, you will get visual information linked to auditory information. So that should allow the coupling between these two modalities, and that should give information to the auditory system. Obviously,
so for the next... Go ahead,
sorry.
please.
No, sorry, go ahead.
No, so for the next conference, we should all do localization tests before and after, and see if we've learned AltSpace listening now.
Yeah, I think there might be actually some effect, depending on the time spent on the conference. Obviously.
I see. Okay. I guess we would have time for another question. Otherwise, I think we can switch over.
Thank you very much.
So, thanks again for your talk. Thank you. Hey, Matt. This was strange. But now it seems to work again. Yeah. Good.
Yeah, whoever sees Stefan first, we can ask him to go on air.
Maybe he's here and we just can't see him.
Here he is. I think I see him.
There he is.
Here.
Can you hear me? Oh, hi. I was there all the time, so.
Okay.
So Stefan, did you select on air on your host tools? And also
Yeah, it should be on air. So go on air and amplify my voice.
Great.
So is it good? Can you hear me?
Yes.
Perfect. Nice. Nice. So I see smiling faces. Perfect.
Let's wait for another minute and then.
Just one more question while they're sitting up. Does everyone in this room see these slides?
So I
Oh no.
No. No. Okay. I'm gonna reset one more time. Once more, do people see the title towards transfer plausibility? Looks like they have.
That looks much better.
Nobody?
No.
Because I don't see them either right now. I don't know. Strange. Let's see.
So Stefan, you're not seeing.
Mixed reality audio and complex scenes. And Stefan, the stage is yours.
Yeah, thank you, Niels. Thanks for the introduction. So, yeah, first we have a really long title. So to wrap up this a little bit, what we basically did was we had a look into how the presence of real sources influenced the ability to detect rendered sources. So, but to explain it a little bit, I wanted to start a small introduction. So, what you're doing when you're evaluating rendering sources, how good or how well they're perceived compared to real sources. Here, doing the evaluation mostly with the paradigms of authenticity or with plausibility. So on the one hand, you have authenticity, which is really is a perfect physical reproduction. This means if you have a real source and you're reproducing this real source over headphones, then this is then the reproduced source is the identity, so it's the same as the real source in the room. And what you kind of do, and when assessing this kind of test of the authenticity, you basically have a real source, you place it in a room, and you reproduce this source over headphones. And in authenticity tests, for example, you can switch between a real source and a rendered source. And basically, what you then have to determine if this is basically sounding the same. But this kind of test has some sort of issues. So it suffers from a ceiling effect, because in authenticity or in the direct comparison, a really small deviation from the real source to the rendered source can be detected. But this kind of definition is a really strict definition, and it's mostly not necessary when reproducing real sources. So there's another paradigm which is called the plausibility. And plausibility means that it is plausible in terms of an inner reference, or another definition would be that a simulation is in agreement with the expectation a listener has towards a real scene. So it's not about the comparison, but it's more about the expectation. And this kind of test is also done in a similar way like the authenticity. But you mostly have, you don't switch, you can't switch between them, for example, but they will be presented one after another. So it can be presented a real source and then a rendered source. And what you have to do is to determine whether this source was then a real source or it was a virtualized source. But also in this kind of tests, you just have the presence of one source. So you have one source, and this source can either be real or it can be a rendered one. So what is a little bit more, the case which is more practical in some kind of way in mixed, for example, in mixed reality, is that you have real sources coexisting to virtualized sources, and therefore we ask us the question if a listener or if somebody can detect virtualized sources when real sources are playing alongside this this virtualized speaker. And also this kind of like allows for controlled comparison. So this is basically comparing to the normal plausibility tests we have. We can control them as we have concurrently playing speakers alongside the virtualized source. And that's why we call it transfer plausibility. So that's just a little bit of the explanation what we wanted to assess. So I will start right away with the technical setup. So what we did to assess this test, we used a reverberant room, so it wasn't done in an anechoic room. And it has a reverberation time about 400 milliseconds. And we used 8 channel-like speakers, and we can see how they were placed in the room by 1, 2, 3, 4, 5, and so on. And also we used then open headphones just to minimize the influence on the resources of the headphones, and also to account for head rotation or to account for a little bit deviation of position. We included dynamic head tracking, which we realized with the HTC Vive system, as the HTC Vive system can provide a 6-stealth tracking or 6 degrees of freedom tracking, and also has low latency and should be really accurate. So now to the modification we made to the headphones, we can see them on the right side. So basically it was just a removal of the front and the back part of the cushion. And this then should provide more open headphones, or should lower the influence of these headphones. And this was also done by Niels, our session chair today. So everybody who's interested should have a look into it. And further, what we then did, we also had a compensation filter, but we used non-individualized compensation filter for the headphones, as I have to make it clear, the aim in this test was not really to have a perfect reproduction, and therefore we just went with the non-individualized filter. And this filter was then just measured with a KU100 head, and we did in total 24 measurements, took the average, and then derived a 256 samples minimum phase filter from it. So what we also did to include the properties of the room is that we did BRER measurements, but we just used one single BRER for every of the 8 speakers. And this was kind of like measured that we just were facing the frontal direction. So we were sitting in the seating position, then looking towards the speaker, and then measuring the binaural impulse response. And again, this one was not individualized. So we used the same impulse response for every of the participants. But what we did a removal of the direct part. So as we render the direct part dynamically, as we include the position, and we include a binauralizer and so on, we did an adjustment of the energy. So we adjusted the energy, the DRER, so the direct to reverberation ratio of them. We adjusted it of the simulated to the same ratio that the measured has, as the DRER is one of the clues, you have when when localizing a sound source. And we also did a time shift so that the early reflections and so on and the reverberant part is arriving in the same time after the direct path when comparing it to the measured BRER. So what we then ended up was kind of like we had then two different rendering methods we used. So we had HRTF rendering, which is called here HRTF rendering, and we used for this rendering we used the headphone compensation and also the dynamic rendering of the direct pass. And we did no externalization in terms of including the early reflections or the reverberant part, and opposing to this, the better rendering technique, which is by far not perfect. As I stated before, there we included the measured early reflections and also the reverberant part. But also this was just static edit, so for the reverberant part or for the early reflections, there was no adjustment made when moving your head or something. So now to the test itself, what we then ended up was different rendering qualities and a varying scene complexity. Now we're coming to the scene complexity. And scene complexity, we're referring it to as 1, 2, 4, or 8 speakers can play simultaneously. And here, one speaker can be virtualized. This means when one speaker is playing, it can be virtualized or it can be real. Or in the case of 4 speakers, 3 speakers are real and 1 is virtualized, or also all of the 4 are real. And we also use different stimuli, so we use music. So we use music from the same track, and these were 8 different instruments. And we also use speech with 4 different languages and with male and female speaker respectively. And we also used the pulse pink noise, which was basically an amplitude modulated signal with 8 different frequencies between 1 and 3 hertz. So on this slide, we can now see the graphical user interface we used. And what we can see is the green dots, and these are the active speakers which are playing. So in the case now of 4 speakers, 1, 2, 5, and 4 were active. And this was kind of like to avoid the confusion so that the participant always knew which of the speakers are now present. So in the case of just one source, it looked like this. And what we also did, so we had to get rid of a memory effect. We also did a randomization of the speaker position. So this meant in the case of just one source is playing, it could change from one to another, from the 4th source to the 1st source. And also randomization of stimuli. So this means in the first trial, the 4th speaker could play back a female French speaker, or also or then in the next trial, it could play back an male German speakers. And what the participant basically had to do, he had to choose which of the sources is virtualized. So if you think one source is virtualized, he had really select which one of the sources is virtualized. And if he thought that all sources are real, he had to just click the real button. But this was kind of like now a long explanation. So right now we will share a demonstration video, and I would say if you have headphones, put them on, because we did a binaural recording of that. And what you will see, you will also see on the left lower side, you will see which speaker is active, and also the right answer will be indicated.
Welcome. You're about to hear part of a listening test. The task of the test was to determine which sound source was reproduced virtually over headphones, while the others are reproduced by real loudspeakers in the room. We will show you the correct answer after each trial. Note that in some cases, only real sources were present. The recording was made using binaural microphones.
So now hopefully you have a little bit of an impression how the listening test looked like, and that it could be really hard to determine which one of the sources is virtualized. So now to the listening test itself, we split up the listening test into sessions. So we first had a training session with 10 trials where the participant was then trained on the different scene complexities and the rendering method and also on the stimuli, and they were also told when they heard an example which one was the right answer and which rendering technique was used. And the session itself then consisted of, the listening test itself then consisted of 2 sessions with each of 48 trials, and in each session we have 24 rendered trials, so where a virtual source was present, and 24 trials where no virtual source was present. And the first session was just made up of HRTF rendering, and the second session was this BRER rendering was used. And the participants were always told beforehand which rendering was used. And also we had no time restrictions, so they could take as long as they want to guess which of the speakers virtualized or if all are real. And they could move their head freely, so they really could look over the shoulder, could go a little bit around, but not too much, but have to stay seated. But they really could not turn on the chair. And luckily, we had the chance to conduct this listening test a second time, because in the first test, Corona hit. But in the second time, we were able to have 15 participants, and 3 were female and 12 were male. And all of these participants can be recognized as experienced listener, as they're all working in audio or in a spatial audio field. So I will go now right on to the results. So what we can see here now from the results is the mean of right answers for different scene complexities, so for different number of concurrent playing sources. And on the left-hand side, we have the first session, the results of the first session. On the right-hand side, we have the results of the second session. And the plots itself are made up of 3 parts. So on the left-hand side, we only included the results where a virtual source was present. In the middle part, we only included the results where only real sources were able. And on the right part, we then combined both of the results. And we can see that even and the dashed line is just the chance level for 1, 2, 4, and 8 sources playing. And then we can see even for HRTF, we see a decline in accuracy. So we see that it just declines from about 100% of right answers down to approximately 63% with 8 sources. And this is even for a really basic rendering. So this should be really a baseline rendering what we had here. And this effect is even more dominant for the BRER rendering. So we have kind of an offset towards less correct answered examples or less correct answered trials. But what we can see here is still that is above chance level. But this should then also be can be due to the fact that that we use basically it's a mediocre rendering. But what's kind of interesting is if you look at the only BRER, so the only virtualized samples for the BRER rendering, we can see that it's easier to guess if a source is virtualized when 2 sources are present. So when a real source is playing alongside a virtual source. So because for only 1 source is playing, we see that it is at about chance. So it is harder to detect virtualized sources without the presence of a real source. But this effect then vanishes if we higher the scene complexity. So on the next slide, it's again the mean and, oh, sorry, I didn't set that as the confidence interval before. So this is also a 95% confidence interval. And what we have, again, is for different stimuli. So what we can see from the plots is that for music and speech, we basically have the same accuracy or the same rate of correctly answers. But for pulse peak noise, this deviates a little bit. So if you look at the HRTF rendering and the middle plot, so for the results where only real sources were active, you see that the detection rate is lower compared to music or speech. But this could already be explained with the influence of the headphones. So what we saw or what we had was some kind of a shadowing effect of the headphones when turning the lateral side towards a playing speaker. And this then sounded a little bit like the source's virtual, so it sounded a little bit weird. But yeah, right. And then for BRER rendering, we even have the opposing effect. So for BRER rendering, we see that the pulse peak noise in case of only virtualized sources, we see that the detection rate is much higher compared to music and speech for pulse peak noise. But this was mostly due to the coloration, as the early reflections and the rear and tail would introduce some coloration, and then it makes them much easier to detect a virtualized source. So for the next plot, we see basically the BRER rendering, but it's a little bit more detailed. So what we can see here, so we have from the first arrow, or the upper arrow is pointing at the real playing source, but it was guessed as a virtual source, and this is for one speaker. And in the more dominant, so sorry, perhaps just say the color. So in the outer ring, the darker red is a real source playing, but it's the amount of these resources playing detected as a virtual source. And the a little bit brighter orange or red is a virtual source, which was then detected as a real source. So this means we have kind of a bias towards a real source, so we are more prone to detect a virtual source as a real source. And this was also observed by plausibility paper or plausibility evaluations before. But if you now look at two speakers playing, so if we add one speaker alongside the one speakers playing, this bias then vanishes. So now they are basically the same. So we have not really a bias towards a real or a virtual source. And if we even then higher this complexity, this bias vanishes. So we can see that then the amount of real sources estimated as virtual is a little bit higher, or is higher, and then this bias for just one source then vanishes. But this could then already also explain with a little bit of the confusion with participants, because in the case of 8 speakers, often there was a lot of confusion, and then they just clicked on some of the parts of the GUI, and this was more prone to just click on a virtual source, just to detect a virtual source. So what we then had, we then had a couple of observations we made during the test that have to be, looked into or have to be taken into account, is also the use of stimuli. Because what we saw is that in some cases there were stimuli, so there were some stimuli which sounded like a virtual source, even if they were real. So this was, for example, there was a saxophone which had really just is playing an onset, and this was often just guessed as a virtual source, even if it was real. So perhaps this has to be taken into account. And also the influence of the speaker position. So if they're a little bit nearer to the listener or further away, but I think we should have minimized this effect by randomizing the speaker position. Also, in some cases, the influence of the tracking system should not be neglected. So normally the tracking system was really fast, and this should not be detected. But in some cases, it seems that the processing power was a little bit low, and there was sometimes delay introduced, which then also helped to detect the virtual sources. And also the influence of the headphones should be recognized. And what we also seen, or what was seen when we looked into the particular results of form participant, is that we have some kind of a learning effect. So with an ongoing time, the listener seems to be more seems to identify virtual sources more reliable, and this could also be due to the fact that they were all experienced listeners, and after a while they just know which cues to listen to. And also one question is, for a high complexity, if the main effect is just spectral masking. So if the detection rate or the main effect is spectral masking, but this is kind of like a thing somebody has to look into in the future, and we did not do this in this paper. But right on now, just to summarize this, what we did in this test, we did more or less a framework for the transfer, what we call transfer plausibility, because I think there's room for discussion for this kind of naming. And we could also have a reduction of the ceiling effect. So we did not really have a ceiling effect, even if we had a control comparison, and this reduction in terms comparing it to an authenticity test. And our results we had, they suggest that we have a lower identification rate when we are using more real speakers concurrently playing to virtualized sources. So this could also then mean that we don't have to use perfect rendering when we are in mixed reality or something and we have concurrent playing real sources. And what then could also be done as an outlook for further research is perhaps use native listeners, how they react to this, because right now we just had experienced listeners and they were all they knew which clues to listen to. And also basically with better reproduction method, as I said before, we didn't use, it was just a mediocre reproduction, but this also resulted in relatively good results, I would say. And what should also be included in future work is signal detection theory. So we wanted to include the signal detection theory, but this was more like due to time reasons, and we would then plan, if we further investigate this, we would then include this. And with this, I'm done with my presentation, and thank you for your attention, and I'm open for questions.
Thanks, Stefan. So do we have any questions from the audience? Once the raise hand button has appeared. Does not seem like it. I'm not sure if raising the hand is possible already. But, someone raised. There's someone back there.
Yeah.
I'm not sure if I can.
Yes, let's just wait a second and see if Dustin will amplify your voice.
So for some reason I'm not able to...
Can I do it too? No.
Let me just wait 1 second and check.
Our technical chair has left.
Yes. Oh.
It is late in the conference.
Yeah.
Well, let's have. Was that Maximilian asking the question?
I think so.
Yeah. What?
Wait. I'll make sure I can hear you, and then I'll repeat it.
That's a good idea. Thank you.
Where are you? There you. Hi.
Oh, here he is.
Okay. Go ahead. Hi.
Sound directions very different
Okay.
compared to yes.
Okay. I think I can repeat
That's my
that.
question.
Thank you for your question.
I think I just put him on air also, so
Yeah,
in case you can't
I heard a
remember the
little
whole
bit of
thing,
it.
he could say it again.
So I was wondering about the impact of the head movements. If you could observe any differences between people who had their head almost static or people who moved all the time. So because of two impacts of the tracking system on the one hand, on the other hand, because then you perceive directions differently.
Definitely. I think so that that the people who really moved around along and really tried a lot of positions and a lot of movement were able to easier detect the virtual source. So this is kind of like also a thing then I thought about afterwards, because perhaps it should have been done that the rotation or the amount of rotation you can do should be then just a little bit more strict. But I think there was an effect. I can't say it for sure, but it seems like yeah.
Wasn't there even logging of the directional data that could be looked at?
Yes, I think so. Yes, but I have to look this up. I still have the data.
Okay.
But yeah, but it seems like because it was like I was in the room and just observed the participants, and it seems like the people who were really into it to detect the virtual source did a lot more movement, and then were more able to detect the virtualized source. Yes.
Thank you.
Great. Thank you. So I guess it's 10:30, at least here in Central Europe, and time to stop. Thank you all for listening. Thanks to all the speakers for the interesting talks. Yes, and one more round of applause, of course, here for Stefan. All right. Okay.
Applause for the session chair.
Yeah, and thank you, Niels, also for chairing the session. Thank you very much.
Thank you. So enjoy.